today we're going to be talking about the basic idea of integration. So this is where integration comes from. Let's consider the problem of finding the area under some arbitrary curve. So let's say I have just some function, call it f of x. And let's say I want to find the area from here to here, called from A to B. Well, how could I do that? So the issue arises that if I were to kind of imagine, if I were to pick up this piece here, we would have something that looks like this. And there's not really any good way to find the area of that figure, right? It's some arbitrary figure here that we don't know the area of. We do know the area of a rectangle, for example, triangle, a circle, but something like this, we don't know the area of. However, one thing we can do is we can obtain the approximation of the area under the curve from A to B. So what we like to use is actually a rectangle to approximate the area under the curve. So what we want to do, the idea is what we want to do is we want to choose evaluation points of f of x between A to B that define the height of our rectangle. And then what we want to do is construct a sequence from x sub 0 to x sub n, where A is x sub 0 and B is x sub n. And we want to choose that to be almost the width of our rectangle. So I could say that from x sub 0 to x sub 1, that's one rectangle. X sub 1 to x sub 2 is another rectangle. And so on and so forth. So we know that the area of a rectangle is equal to the length times width. This is the width and this is the length. So let's define the width to be x sub I minus x sub I minus 1. For example, if I put I equals 1, the width is x sub 1 minus x sub 0. And we could see clearly here that x sub 1 minus x sub 0 will give me the width of this rectangle. But how would I find the height of the rectangle? Well, I could choose any point between x sub 0 and x sub 1 to be the height of my rectangle, including x sub 1 and x sub 0. So let's also define the length to be f of x sub I bar, where x sub I bar resides in the interval of x sub 0 to x sub 1. I'm sorry, that was wrong. X sub I minus 1 to x sub I. So for example, for the rectangle from x sub 0 to x sub 1, I'm going to call it f x sub 1 bar, and that will give me the evaluation point somewhere between x sub 0 and x sub 1, inclusive of x sub 0 and x sub 1. So notice here, when I use these rectangles, it doesn't give an exact area, right? we have some area here that's not filled in. So that's an issue. However, the approximate area of f of x, if I were to take each rectangle, the area of each rectangle, and I were to sum each one up, I could say the area of f of x is approximately the sum from I equals 1 to n of f of x sub I bar times delta x sub I. So the question is there some way I can obtain an exact area of a function under the curve? Well, yes. What we have to do then is decrease the width of the intervals to the point where choosing evaluation points is going to be such a tiny interval to choose it that it wouldn't even matter. The change between, let's say, x sub I or x sub 1 bar and I'm sorry, that wasn't good example. If I were to like have the interval x sub 0, x sub 1, x sub 0 would be less than or equal to x sub 1 bar, which would be less than or equal to x sub 1. The change between the height of those points would be very little, that it wouldn't matter. We could obtain an exact area under the curve. So we will say the function f is integrable if and only if we can find a delta greater than 0 such that, I'm going to go to the next screen, the max of our widths of our rectangles, so x sub I or delta x sub I, such that I is in 0 to n. So in other words, I'm going to consider all the widths of the rectangles, take the max of it. So we're saying if that's less than delta, and if that implies that our sum of the approximate area under the curve minus the area of f of x is less than epsilon for all epsilon greater than 0, we could say that it's integrable. So what does that mean? Well, what it means is if I could pick a delta where the max of my widths are less than that, and if that implies that my approximate area minus the area is less than epsilon for all epsilon greater than 0, that means that we're, in essence, this guy is approaching this guy. So we could say that then the area of f of x is equal to what we call the integral, if that's the case. So we'll say the area of f of x is equal to the integral from a to b of f of x dx, where the area of f of x is equal to some number m in R. So that's the condition for our sum to be a good approximation of the area of f of x. And if this condition holds, we say that the area of f of x is equal to the integral here. So one way to think about it is that this becomes our integral at some point. So to illustrate the idea, what we could do is look at an example. So prove the integral from a to b of f of x dx equals c times b minus a if f of x equals c. So what we can do is, again, let x sub 0 to x sub n be a partition from a to b. Therefore, we could say that this sum is equal to the sum of c times x sub I minus x sub I minus 1. I'm going to go to the next page, which is equal to c times f of, oh, my bad. Try to erase it. X sub I minus x sub I minus 1 from I equals 1 to n. So I factored the c out. By properties of sums, we can give each term in the sum its own summation. So let's rewrite this as c times I equals 1 to n of x sub I minus the sum from I equals 1 to n of x sub I minus 1. So what I'm going to do is I'm going to pull out x sub n from this sum, and I'm going to pull out x sub 0 from this sum. So let's rewrite this as x sub n plus the sum from I equals 1 to n minus 1, because I took out x sub n of x sub I, minus x sub 0, minus the sum from I equals 2, because I took out x sub 0, to n of x sub I minus 1. So if we were to look at these two guys, it's clear that the difference between these two would actually be 0, so they'll just end up canceling each other out. So therefore we have c times x sub n minus x sub 0. Well, I defined before x sub n to be b and x sub 0 to be a. So this is equal to c times b minus a. So if I choose any delta that satisfies the interval condition, in other words, I can't choose my delta be larger than b minus a, because then it would be outside the interval. But if I were to choose anything within that, I would speak it's clear that the max of x sub I, delta x sub I, be less than delta would imply that the interval of a to b of f of x c times b minus a. Thank you for watching, and have a good day.